Okay, so it's time. So let's start. Welcome everyone to this Thursday's seminar. So today we have Federico Zerbini, who will sort of tell us maybe a little bit more in depth about stuff that was discussed this morning. So on single value periods in string theory. So please go ahead.
Okay, thank you very much for the introduction and the invitation. I'm very happy to be speaking here. So this is some kind of overview talk over some progress that have happened in the last, say, 4 years. And it's, in a sense, it's a continuation of some talks that were given during the first and the second workshop here. So there was a very nice series of lectures by Oliver Schlotter on string theory amplitudes. And this, if you have followed that lecture, is kind of, I'm going to go more in depth into some aspects of that. But I'm not going to assume anything. So I recall everything I need for the talk, both from the physics side and the mathematics side. Since I can't, I mean, it's been several years now that I've been working on this string theory amplitudes, but my background is still a little bit shaky on the physics behind this. So in case you have some tricky physics question, maybe I'll try to give back everything to our expert.
What is the vacuum?
So there are physicists that can help me. Okay, so let me start. Try maybe take the mouse on the. Oh yeah, okay. Good. So in the quantum world, if we have an interaction of, let's say, two particles, we cannot really tell what happens between these particles. So we would like to know where they go and when they arrive at this point, but all we can do is to measure probability of this interaction, and this is what is measured by scattering amplitudes, in a sense. So the idea that one of the ideas to compute scattering amplitudes is goes back to the 50s, I think, or 40s, and this is Feynman's perturbative approach. We have heard of this already this morning, in fact. And the idea is the following. So you kind of try to imagine anything that can happen in here, and you associate a probability to every kind of interaction, and then you sum over them all, weighted by some constant to some power. And that's the big idea. It's some kind of perturbative expansion. So it's a power series which is badly convergent, as Daniele mentioned, and one has to make sense of this. And all the integrals, I think, are also divergent. So it's a divergent series made of divergent terms. Okay, so the probability of each of these graphs, which are also called diagrams, Feynman diagrams, is computing by an integral, divergent integral, which is called a Feynman integral. And the reason of the success of Feynman's approach is the fact that if you can compute just a few of these Feynman integrals, the easiest one in a sense, because the level of difficulty is measured by the number of loops that arise in here, and loops are essentially creation and annihilation of particles. So if you can compute the very first ones, so the easy one, and just few of them, then you have really a very precise approximation of the amplitudes. So it depends on the process. But that's the method that was used, for instance, to discover the Higgs boson. So here, so all these pictures I've taken them from a paper of Francis Brown. So if he's listening, thanks to him. I think here the black dots are the experimental data, and then there is a blue line which is called the background, and this is computed by tons of Feynman integrals computations, and assuming that there is no Higgs boson, and there is this bump, and this means there is a new particle. That's the idea of how to interpret this graph. And of course, the experimental computation in these particle accelerators have a lot of are covered by the media and everything, but people who compute these background lines, the blue ones are equally important. Okay, so I'm going to tell you about the blue lines in the context of, well, let me first say something more. So why is this interesting for this program? Well, because this is one of the main sources of interaction between mathematicians and physicists, and in particular number theorists and physicists, because there are very interesting numbers that appear in the computation of these Feynman integrals. What are these numbers? So the first one is, yes.
So you say you have this infinite series, and then you get your data from that. But how do you know where to stop? So how many integral Feynman graphs do you have to take into account to get a good fitting?
It depends. So it depends how big is your coupling constant, for instance, or your constant that is weighting this kind of.
And are there some precise rules, or is that?
There are no precise rules. You compute as many as you can, and then you compare with the data of their accelerators. And if the data are pretty close, then yeah,
Then you stop.
Sorry, I don't think that's precise. So you're expanding for electrodynamics, you're expanding in terms of the structure constant, which is 137.
Yeah.
So at successive orders, everything is down by 137. So you don't have to go very far before you get precise.
But then
the
coefficients.
Exactly.
The coefficients also change, but basically, as you go to higher orders, the successive contributions become considerably smaller. And what happens is that the experiments become precise, so the numbers go. For example, if you calculate G-2 for the electron, that's now known to, I don't know, 12 figures or something, and so you have to go to one higher, 5 or 6. I think 5 or 6. But basically, you know how far you want to go.
Thank you. So what numbers appear? Well, it was clear since the beginning that these kind of numbers will appear, so special values of logarithms at positive integers, and the special values of the Riemann zeta function at positive integers. So for instance, they appear in the computation of the anomalous magnetic moment of the electron. And more generally, extensive computations in the 80s and 90s show that you get a lot of this kind of multiple series called multiple zeta values, MZVs, which in a sense generalize these special values of the Riemann zeta function. So and the NIs are positive integers, and you want the last one to be bigger, equal than 2 to have convergence, and that's how they're defined. And but you get something more. So at some point, people were asking themselves, "Are we going to get only multiple zeta values?" And the answer is no. And for instance, you will get periods and quasi-periods of elliptic curves and of modular forms. So a lot of these computations are due to people like David Broadhurst. I think I should be giving credit here. Broadhurst and Kramer. The 90s. And well, here I said you get periods and quasi-periods, and in general, the reason why you get interesting numbers of this kind is that Feynman integrals are periods. So what are periods? Periods are complex numbers so this is an elementary definition of periods. We'll see another one later, but they're complex numbers with both real and imaginary part, given by absolutely convergent integrals of rational functions with rational coefficients integrated over a Q semi-algebraic cycle. This just means this is some domain specified by polynomial inequalities with rational coefficients. Okay, so Feynman integrals are interesting numbers, except that this is not quite correct. They're not really numbers. Usually they depend on kinematic parameters. To their functions, but still as functions of the parameters, so they depend algebraically on the parameters, and so they're something called period functions.
What is semi-algebraic?
Well, this is a way of saying what I said in words, that your domain is specified by polynomial inequalities instead of equalities, and then I demand a rational coefficients of this polynomial.
So the boundary is a real algebra.
Okay, so yeah, this is a kind of elementary definition that is due to Kontsevich and Zaghe, but periods were known before, and they're more classical objects. Good. But today I would like to tell you just about string theory amplitudes. Well, because in a sense it's much more beautiful mathematically, so you can really see some structure there, and also it's very much related with this theory of single value periods, which is probably the main topic of this talk today. So, well, string theory, very roughly speaking, you can divide strings into two kinds. So, a string, if you want, you can think of a string as something generalized. So you have point particles giving you Feynman diagrams in quantum theory. And now you want one-dimensional objects, strings, which are these red things, and they can be either open intervals, so open strings, or closed intervals, closed strings. And well, and this is what the Feynman diagrams look like if you just take a point and make it become a string. So there will be some interaction between this string and this string, something will happen, and well, this is one diagram, so nothing really happens, and then here you have something happening more complicated, and then something more. So what before used to be loops, now they're kind of holes into surfaces. And of course, the topology in the open and the closed string case is quite different, and there are also more complicated topologies that I'm not going to discuss. So I will simplify a lot this discussion today. So it turns out you can think of these particles, you can shrink them, and think that geometrically as point on your surface. So in the open string case, they're generating a surface with boundary components, which are these ones. And so they will be on the boundary of some disk here, or sign, annulus here, and so on. And in the closed string case, if you just shrink this, you will get a two-dimensional surface with marked points. We get a sphere and then a torus, and a torus with two poles, and so on. And apologies if this looks like this, but this is a sphere, points on the sphere, and this is a disk, points on the boundary of the disk. Well, I didn't mention this, but you can also think, so physically you can think of open strings as describing, so in the limits they're describing certain gauge theories, while closed strings, they're describing gravity. So this is the vague idea you should keep in mind. So, so today I'm going to talk about relations between open and closed string amplitudes, and this means that there will be a relation between gravity and gauge theories. So this is something very interesting. Even if you don't believe in string theory, then this kind of relation still holds in their limits, and so still holds for quantum theory limit of string theory. Good. So let me say something about the state of the art without really defining too much of, and then later on you will understand the meaning of most of these words. So as I said, so to each topology, as in the quantum theory case, you associate a Feynman integral. Probably I shouldn't call it a Feynman integral, but let me say this anyways. And this is a function, so it's either for open or closed strings. It depends on some kinematic data that we call S, so it's a function of S. And then it depends on the genus and the number of strings. So the genus of the surface I'm considering, and then one has to be a little bit more careful here in the open string case.
In the open string case, does it mean it's the number of disks you remove from the
Well, but it's more complicated than that, because there are also non-orientable surfaces you have to take into account. But let's just imagine that. Yeah, that's just okay. So good. So then what you do is the amplitude of the string theory. So the string theory amplitudes that you are considering will then be given, as in the Feynman integral expansion of the amplitude in quantum field theory, by this kind of infinite series, which is now indexed by the number of loops of the surfaces, Feynman diagrams. And then it is given in terms of powers of this GS, which is the string coupling constant. Okay, so what we would like to understand are these coefficients. And as I said in the quantum field theory case, so what you would like to understand is just in the beginning, the very first of them, so just a few of them. But in principle, you would like to understand all of it and even maybe the non-perturbative part. That's something for the people in the other program in research. Good. So this is the state of the art. We know a lot of things about genus zero, and that's what I will explain. Today I'd like to focus more on genus zero because we know more and we can prove stuff. So the Taylor coefficients, if you expand in these kinematic data, so this depends on some momenta and the string tension of the string. And so if this tends to zero, well, this is many variables. If they tend to zero, then what you recover is some kind of quantum field theory limit, and the Taylor coefficient gives the string corrections to this quantum field theory limits. And these are the things that people have been trying to compute in the last maybe 10 or 20 years. So in genus zero, you get multiple zeta values. In genus zero, for closed strings, you get something called single value multiple zeta values. So you have heard of them already, but I'm not sure we have ever seen some definition of them. So today I'm going to try to tell you something more about them. And in genus one, well, we have heard a lot about modular graph functions during the workshop and also a little bit today with Daniele. So this is for the closed string amplitudes, and I'll tell something about them. But also in the open string case, there is something interesting happening. So there are things, generalized multiple zeta values called elliptic multiple zeta values, or you can express them in terms of analogs of the modular graph functions, which are called homomorphic web functions. And all of these can be written as iterated Saclay integrals of Eisenstein series. So this is something I'll try to mention at the end of the talk. Good, and then higher genus, I'm not going to say anything today, but there are analogs of modular graph functions in the closed case, and as far as I know, nothing is known in the open string case. But today we would like to say something about the relations between open and closed strings using this theory of single value periods, and this should it's expected to hold also in higher genus, even though we don't quite know how to compute the amplitudes in higher genus.
So nothing is known because we don't know how to do it, or because no one has gotten there yet? Or there's some conceptual...
I think, okay, so this is a question for somebody like Eric Docker or Oliver Schlotter. But I think Schlotter told me that he has hope that one can compute the genus 2 open amplitude, and it's just that people didn't do it yet. So even in the genus 1 case, the closed string side was computed much before the open string side, because mathematically the objects that you encounter are simpler on the open string side, but to define the integral physically, it's much more complicated to define the open string, because it's defined out of the closed string one by some kind of procedure called the method of images, and then you have to, probably there are complications due to supersymmetry that I'm not really... Okay, so is there any question about this so far? Or can I go to genus 0? Good. So in genus 0, I want to present first of all the 4-point case. It's super instructive and it's very simple. This was already studied by Oliver in the first workshop, but still I think it's a good idea to recall it now. So in the open string case, the 4-point, so 4-point means 4 strings, case is what is called the Veneziano amplitude. This was studied in 1968, and this is in fact the birth of string theory is out of this Veneziano amplitude. So this is a very important object for string theorists.
I can make a comment. Yesterday was Veneziano's 80th birthday, so there was a conference in his honor.
I see. So, I mentioned at some point, I mean, I never told you anything about the integrand of this amplitude thing, but the integration domain, I told you this should be some kind of moduli space of G0. I mean, this kind of worksheet generated by the four strings. So why is this equal to the interval 0, 1 in this case? Let me go back. So this is the thing we would like to integrate on. So you think of this, in fact, as a real line, and you have four punctures, and you want to integrate over these four punctures and their order, but it turns out that there is some symmetry you can use, and then and you can fix three of these 4 points at 0, 1, and infinity, and the fourth one is going to vary between 0 and 1. So that's the integration domain that you find here. This is the integrand. Well, it's related to these wing functions that were mentioned today by Daniele. And it's very, I mean, this is computed by Euler, so this is the beta function. It's a quotient of this product of gamma function. And it's also well known by, again, formulas due probably to Euler, the Taylor expansion of gamma functions, and this gives you the Taylor expansion of the amplitude for these S and T, which are the kinematic parameters that are that enter into the 4-point computation. So there are only 2 of them. So by the way, I should mention these are massless string states. Good. So okay, it's a very beautiful formulas. Here you can see these Riemann zeta values. And what about the closed string case? This was studied just 1 year later by Virasol. And so here the integration domain is, well, you should have M04. So that's really M04. You have Riemann surfaces with 4 mark points. And as you know, M04 is just P1. So you can fix, again, by symmetries, 3 of the points at 0, 1, infinity. So this should be a P1, C minus 0, 1, infinity. And you come back to find again this. Well, the integrand is different because now the Green's function is different. And this was a computation due to Shapiro, I believe. I'm not sure that Virasol did this. And again, you have this quotient of gamma functions, and again, you can use the Taylor expansion of gamma functions to get this kind of formula, which looks very similar to this one. So I wrote it in a very strange way, just to underline the fact that they're very similar. So these are only odd integers, and then you get again the Riemann zeta values, but just for the odd ones. And then you have a times 2. Okay, so how do you relate now these 2 objects, and why can you relate these 2 objects? So this is the main question that we asked first. Okay, it's pretty obvious if you look at this gamma function products here. So this is just equal to this, and then you have something very similar. So A closed is just equal to some prefactor times A open, and then A open at minus S minus T minus 1. It's completely obvious if you look at this formula for longer. Should have been maybe on the same slide. Then if you apply Euler's reflection formula to the gamma functions, then you can write it in an even nicer way, which is the following. So you have closed string amplitude, which is in a sense the square of an open string amplitude. So this is what people call double copy relations, and this is something that holds in more generally, as we will see, and also in the quantum field theory limit. And this tells you that gravity is a double copy of HT. Okay, so this generalizes this formula. Kawai, Well, and Tai realized that in 1986. They were able to write the closed string amplitudes as quadratic expression in open string amplitudes. So here you don't quite understand what I mean because I was kind of cheating. So for the 4-point case, there is just one amplitude, A04, open and closed, but for n points, there's a vector of them, and then you have to use all the components of the vector. But anyway, so there is some kind of quadratic like this expression of closed in terms of open. And as I said, then gravity is supposed to be a double copy of H series. That's how people realize that. And now I would like to tell you how this theory of single value periods, or some mathematical theory, explain this kind of double copy relations between gravity and gauge theories. So this is something very deep mathematically, and that's the next part of the talk. So maybe, now I will recall some basic stuff about periods and cohomology in order to define single value periods. So I already told you what a period is in an elementary sense, but period usually is solved by algebraic geometries in the following way. So you have smooth algebraic variety and the normal crossing divisor defined Q. And then you have algebraic Duran cohomology, but relative to D, and Betti cohomology relative to D, which is just the singular cohomology on the complex points. And then the Duran theorem in the algebraic case, which is proven by Grothendieck, tells you that there is an isomorphism once you tensor with C between the Duran and Betti cohomology. And this is just given by integration. So you send a differential form or class of differential form here, at least in the affine case where you have global differential form representing objects in here, into the integral of the differential form over the sine. So this is a map over the Betti cohomology, and it's Betti cohomology. So, and if you choose a basis for the Duran and the Betti cohomology, but this is an isomorphism, it's a linear map, and it's represented by a matrix, and this is called the period matrix. So the coefficients of this matrix are complex numbers, and they are periods in the sense of the previous slide. And in fact, the two definitions are equivalent. So if you define periods in this way, then this is completely equivalent. You get the same ring of complex numbers. And this is quite important for us. As I said, if your periods depend on parameters, then they are periods. They're called period functions if they depend algebraically on the parameters. And because of essentially finite dimensionality of the homology, then they satisfy differential equations, which are called Picker-Fuchs differential equations. So they are solutions of these differential equations, and in particular, in general, they're multi-valued functions. So they will have some monotomies if your basis is not simply connected. And now I can define single valued periods, and the idea is you would like to make these single valued period functions, so these multi-valued period functions single valued. Okay, so you have the starting point is that you have complex conjugation on the complex point of X if your variety is defined over Q. And this induces an automorphism, an involution automorphism of the Betti cohomology, which is called the real Frobenius F infinity. And then what you do is the following. So you have the comparison isomorphism between the Duran and Betti. Then you have these real Frobenius from Betti to Betti, and then you can go back to the Duran by inverting the comparison isomorphism. And the map that you get is an automorphism of the Duran homology that is called the single valued automorphism. To define single valued periods, you need to use this automorphism of the Duran cohomology. So this is again some kind of linear map, linear isomorphism. So it is represented by a matrix, and once you fix the basis, then this matrix is called the matrix of single valued periods. And because it's defined in this way, then it can be represented. Then there is this formula in terms of the period matrix of C. So PSB is going to be equal to P bar minus 1 times P. So each single valued period in particular can be expressed as a linear combination of products of homomorphic and anti-homomorphic periods. So this is some kind of bilinear relation, Riemann-like bilinear relation. Good. So what do we do with this? So first of all, some facts about these single valued periods. So these two are not really important for the talk today, but I think they're kind of interesting. So the first one is that they're real numbers, always. And the second thing is that they're analogs of p-adic periods at p equal infinity. So this is, it's not important if you don't know what p-adic periods are, but so p-adic period, in a sense, I call this f infinity, the real Frobenius, but you also have the usual Frobenius in crystalline cohomology, and you use that to define what are called p-adic periods.
Then, okay, what about finite primes? Is there an analog story of p-adic periods where you don't have, where you're not at the Archimedean place, but you have
Exactly. So here by p-adic, I mean at finite primes.
so that I thought you meant.
So
I
this
misunderstood your
So these are analogs at p-adic equal infinity of what are called the p-adic periods.
Okay, then I
So for the p-adic periods to define them, you need you consider the crystalline cohomology, and there is this p-adic, this Frobenius.
Yeah, thanks.
Isomorphism.
Then it's no longer C, you can tensor.
Yeah, you have to tensor with QP.
Very, very different.
You tensor with QP, and you define this way single p-adic periods. That's one way to define p-adic periods.
Still define it in terms of like intervals as well.
Yeah, so I'm not an expert on this. I think there are things called p-adic polylogarithms and multiples eigenvalues, which probably also have some kind of integral representation. And they fit into this kind of p-adic periods. But there are also completely different, probably, as far as I understand, different periods defined by Fontaine and others, France, and it's not clear what's the relation. So there are various definitions of p-adic periods. So okay. So one important thing for why are they called single value periods? Because if they're functions of parameters, it turns out that they are single valued functions of these parameters. So periods as functional parameters are multi-valued. They solve this Bickerford's equation, and they're homomorphic solutions of this Bickerford's equation. But now you have single valued functions, so there will not be any more homomorphic functions because there will be complex conjugates. But then, so you lose homomorphicity, but you gain single value. And the first example is suppose you have GN, the multiplicative group. So this you can think of this as punctured complex plane M0 relative to the 2 points 1 Z, and the period matrix gives you the logarithm of Z. So this is the period matrix. This is just some computation. I don't expect you to do this in your head, but believe me. So if you take this homology group, then the periods that you get are these ones, and the associated period matrix is this one. So here you see you have the log, which is multi-valued, and here you have log of Z squared absolute value, which is single. And the analog of 2 pi I in single value world is just minus 1. And the second example is take a complex torus. Then you have the period matrix, which is just period matrix of this, which is so this is omega 1, omega 2. These are the periods of the elliptic curves, and then there are the quasi periods. And it's known that if you act the set to Z on this, your period matrix will transform by multiplication with this gamma. So this means that it's not single value as a function of omega 1, omega 2. There is some monodromy which is given by gamma. But if you apply the single value the description and then you act again by gamma, you get PSV itself. And you can see this on the coefficients. This is something which may be very familiar to you. So G2 of tau, where 2 isostentious, you know it's not modular. And maybe probably you know that it's given by the product of period by the first quasi period. So in a sense, this is eta 1 is in a sense equal to G2 of tau over omega 1. This is quasi-modular, and this is described by this equation. Right? But it becomes modular if you apply the SB prescription, and what you get in the PSV matrix is precisely the completion of G2, the almost holomorphic isostensivity. This is some kind of
Integrate second.
Yeah, exactly. So I don't know where this. I think this kind of name comes from. I mean, this is just defined as the entries of these metrics, and these are given by integrating the second kind differentials. The fact it's called quasi-period, I think it's because you can find these numbers by writing down the bias stress zeta function, and this zeta function is not periodic, it's not elliptic, but it's quasi-elliptic, and the failure of ellipticity is given by these two numbers. So I think that's why they're called quasi-periods. So, okay, so in the case of elliptic curves, these are very classical objects, but in the case of modular forms, it's not so. I realize it's not so classical. The quasi-periods. Need to integrate second kind differential forms, but this will be some modular form with poles. Okay, anyway, so let me go back to the topic. So Francis Brown and Clément Dupont in 2018 wanted to understand these KLT relations in physics, and one thing they did to understand those was to look at these single valued periods closely and find some integral representation of the single valued periods, which looks like this. So this is you have to consider this kind of special case. So you have differential forms with logarithmic singularities. Then essentially, if you are in this situation, the coefficients of the single valued period metrics corresponding to omega and mu, which are, let's say, elements of this basis, are going to be given by integrals over the whole, over the complex point of the whole projective variety of eta wedge omega bar. This is some formula that they proved using Bernoulli equality. And so this is a way to write down explicitly as integrals these single valued periods. I mean, of course, we know to write them as combination of products of holomorphic and anti-holomorphic usual periods, but this is just a way to directly write down with integral representation these single valued periods. That's how they look.
So can you say again?
Yes. So this
is define a single value, like as a matrix.
Yeah.
It's but it looks like omega in different.
Yeah, absolutely. So this SV map is this automorphism of the Durham cohomology. So now omega is again a differential form, and this is just the pairing given by writing omega in the basis. So okay. So in particular, the entries of the period, single value period metric will be integral like this, and this kind of opens the door to explaining that things like height pairing or height pairing, for instance, are single value periods or regulators. So things that have this kind of integral representation can be written down easily as single value periods. And the corollary of this is that you have this kind of bilinear relation. So you have an integral over the whole surface, which is a single valued period. And then by the other definition of single valued period, you can write this down as a linear combination of usual period integrals and complex conjugates. And now the coefficients will be some numbers given by intersection numbers of the cycles, gamma and delta, which form a basis of the Betti homology. And well, here we're getting very close to this string amplitude business, because this looks very much like these KLT relations. But let me tell you something more about single value periods before we go back to physics.
Can I ask you a question?
Yeah.
So on the right hand side, these forms are logarithmic. There's non-singularities on visualizer. So how are you doing the integral? So like, what does it mean to integrate them for XC?
Yeah, they have singularity, but you have some condition on the so you can make sense of this. Maybe I didn't write down the condition on the divisors, but the divisors are in such a way that the integral will be convergent. So this is let me see. So we need is this already? So there might be some other condition on the devices, but it's fine. So this integral is going to be convergent. So this is some well-defined. If I wrote down the setting correctly, we can discuss this later.
So a comment. So I seem to remember that in that paper, they have a discussion on that, and they also comment on the fact that there is a paper by Kashtan and Felder, where they are sort of doing similar integrals and doing some regularization and so on. But they say that we don't need that because somehow the setup is in such a way that this is convergent.
Exactly, they do that. Yes. And anyways, you can always pick a representative of differential form which has logarithmic similarity. So you don't really need to do something which has worse similarity and which is integral. But it's really crucial that you have this normal crossing, and that's the thing that they discuss a lot in the string theory, because you don't have normal crossing there, and then you have to do some roll-ups to get the convergence. Okay, and something else. So under certain assumption, which I'm not going to talk about today, there is a natural map that goes from Betti homology. Again, you have these divisors A and B as before. And then you want to go from Betti homology to the RAM cohomology. So there is a natural way to associate to a cycle in here, a differential form in here, if D is the dimension of the variety. And and using this, you can define a single value projection, so a natural way to go from a period to a single value period. And this is just as follows. So you have your differential form integrating over gamma, and you apply C0 to this gamma, and you integrate C0 gamma wedge omega bar for X of C. So this is what people call single value projection in the talks on modular web functions and string theory amplitudes in this program. But you cannot always do that. So there are problems in certain kind of motifs. And okay. An example of this is the following. So if the logarithm of Z, you write this down as the following period integral. And then this natural map, it turns out that it transforms this integration domain from 1 to Z into the following differential. And so this integral is mapped now to this single value period integral here. And if you do this, you get that this is precisely log of absolute value Z squared. So absolute value, so this is precisely the single value image in a very precise sense, log Z. And you can do that for, it turns out that multiple zeta values satisfy these certain assumptions. And so you can define single value multiple zeta values exactly in this way. So you have an integral representation of multiple zeta value, you apply this single value map procedure, which maps this differential form into another, this cycle into a differential form. And what you get is something that you can call the single value multiple zeta. This is not how they were defined originally, but I think it's a pretty clean way to define them, because otherwise the original definition is a little bit messed. And okay, so let me say something about these single value multiple zeta values, because they've come up already this morning and many times at the conference. So they are contained in the algebra of multiple zeta values, and they generate a very small subalgebra. Of course, you cannot prove it's a very small subalgebra because you cannot prove case of this kind of complex numbers. Because you don't know about the relations of these values. But conjectured, this is very small, and the single value version of the even Riemann zeta values is 0, and the single value version of the odd Riemann zeta values is twice the cells. And then all the depth 2 single value multiple zeta values become products of single zetas. So yeah, and then all the and then the first irreducible single value multiple zeta values is in depth 3. So this 353 with 13. And this you can prove is given by this form. So you do get something irreducible, but you really need to go to higher weight and depth. Okay. And the thing is, these are precisely the numbers that were found in the string theory amplitudes computation for closed strings, and also in other parts of physics, also for this multi-range kinematics and the graphical functions of Oliver Schnett's, involve this kind of periods. So this is something that has been found.
Just a different question. So if you write a period as like the integral over one cycle with some form, then you have another cycle with some other form. There's some well-definedness. So can you, is it easy to see that this PSV is a well-defined operation?
It's not easy, but it is. It's a motivic map. So in the motivic world, all these kind of relations between periods. So periods are defined. Motivic periods are defined modulo relations. There is a conjecture of which are the relations that can happen between periods. Now this map respects all these relations. So it gives us the same single value. So to talk about single value periods and periods, you should probably talk about motives first. Let me not. Okay, so let me go back to the state of the art. So it was proven already in 2013 that the coefficients of the open string amplitudes for n particles are multiples of derivatives. So this is well known now, and this is was proven by using methods developed by Terrasoma and collaborated with Röderschlotter and Schwager to prove this. And then in 3 different papers with 3 different methods in 2018, it was proven that the Taylor coefficients of the closed string amplitudes in genus 0 are single valued multiples of derivatives. So this was conjectured by Schwager in 2015. And in fact, Francis Brown and Clément Dupont did more than that. So they proved it. Not only they proved it, but they also proved this formula. So if you apply term by term to the Taylor expansion of the open string amplitude, the single valued projection method I just mentioned, you get precisely the closed string. So this is something that you can see. So if you remember, I wrote these Taylor expansions, and if you send the even zeta to 0 and the odd zeta to twice themselves, you get precisely the closed string. And because of this, then they have from the theory of single valued periods for free the double copy formula. You can express this as some kind of double copy of this, and this is another proof of the KLT relations. In my opinion, a much cleaner one, because the original proof is very complicated. It uses some complex analysis tricks. It's quite tricky. Okay, and maybe also a comment. So in my paper with Pierre, we write down, we prove the KLT relations as specialization of conformal block decompositions. So in conformative theory, you have correlation functions which have to be single valued functions. And there is something called the conformal block decomposition. That means that they can be expressed in terms of products of homomorphic and anti-homomorphic functions, which are called the conformal blocks, which are multi-valued. And then we found an appropriate correlation function such that specializing, you get the KLT relations. And then from that, I mean, on the one hand, you see that you should get something single valued for the closed strings and multi-valued for open strings. But also, it kind of tells you that this conformal block decomposition should come, in general sense, from the single valued period formalism. I think it would be very interesting to explore this. And this should hold, this is also like smoking gun. This kind of KLT relations and single valued period formalism should hold also for higher genus string theory. So this kind of relation functions business is expecting. It should hold in higher genus. Okay, so now in the very last part of the talk, I'll say something about genus 1. As I said, this is not as nice as genus 0. There are conjectures here. Let me tell you something about these conjectures. We can discuss later if you're interested. Or is there any question about genus 0? That's a good point. So genus 1. Now, genus 1, I'm not going to be very precise in genus 1. I wasn't already in genus 0, but I'm going to be even less in genus 1. So in genus 1, your open or closed string amplitudes, which depend on the kinematic parameters, you should think of this as an integral over some kind of moduli space. And it turns out that you can split this integral into a first integral over a moduli space with just one string fixed, like you were fixing 3 in the genus 0 case, you fix only 1 in the genus 0 case. This is because of the symmetries of the problem. And then you integrate something which will depend on a parameter tau. So tau is the modulus which will be integrated in the same integral. So this is also an integral, but it's now an integral when you fix the complex structure tau, and you just integrate over a fixed whatever surface you are integrating with. It depends on open values. And today I don't want to talk about this whole integral, but just on this first integral here, they call I1n. And this is now not giving numbers in the Taylor expansion, but functions of tau. And what functions of tau? Well, there are the famous modular graph functions that were already introduced many times in this program. I think they were, I mean, the name is from 2015 paper of Green, Van Hove, Doker, and Buurthoven. But I think it's fair to give credit to this paper 2008 by Green, Woodson, and Hove. And essentially it goes as follows. I mean, I'm not, but let's say there is a graph which is associated to some multi-index, which gives you essentially the power of the constant variables, the kinematic variables. You associate to this multi-index graph. And then from this graph, you cook up some real analytic modular functions such that the Taylor expansion of this object is like this. And in fact, it's not quite true. Here I put a tilde because this is true only for 4 or less particles. You have something more complicated with more than 5 particles. So modular graph functions are related with these genus 1 amplitudes. They're very important to compute them, but I'm not writing down the actual definition. And in OpenString case, you have something very similar, which I call homomorphic graph functions. They were defined later, as it often happens in string theory. So you first look at closed stuff and then open stuff. So they were defined by myself, Johannes and Oliver in 2018. And again, they're such that some kind of modification of the OpenString amplitude can be expanded in terms of. And I'm not defining them, but I want to give you a conjecture. And that's the end of it. So homomorphic graph functions. So let's pick the very simplest case of graphs, which are the polygon graphs. So in this business, at least, they're the simplest because they have only one. And it turns out that the homomorphic graph function associated to the polygon graph with R vertices is essentially the Eichler integral of the weight 2R Eisenstein series. The classical holomorphic for a cell to Z Eisenstein series. The Eichler integral, this, which is some kind of primitive, it's a no, sorry, it's 2R. Okay, anyway, I'm sorry. So it's some kind of primitive of the Eisenstein series, which has nice modular properties. It's not quite modular, but it's related with these cycles, Eichler theories. And if you take the very first one, the simplest one, the P polygon 2, so with just 2 edges. So these functions has the following asymptotic expansion and decay. So it's already very interesting asymptotic expansion just for the very first simple example of graph. So here T is pi I tau, Q is equal to 2 pi I tau, and you can see these Riemann zeta values here for this first Lohan polynomial, and then something which is big O of Q afterwards. And we studied this asymptotic expansion, and in general, these holomorphic graph functions always have an asymptotic expansion like this, with these powers of T which are bounded by the number of edges of the graph, and with coefficients which are multiples of the values.
So this BP2, how does it transform? Can you write it up?
It transforms essentially as this Eichler integral. So it will have a correct. So it's not quite modular. It will have.
Is it quasi-modular or it's something?
No, it's not quasi-modular. It is an Eichler integral. So it has. So the failure of modularity is measured by itself. So the correction in this case is just its complex conjugate.
Would it be possible to write down this in GTL? Like, what would you mean by?
I think this standard notation could be actually integrated.
Could you write down what the integral is? Like,
So I think one way to define the actual integral is as follows. G QR tau is equal to the integral from tau to infinity. And then here you have to do some kind of regularization at infinity because it's the Eisenstein series of z minus tau to the 2r minus 2 times g 2r of z. So this is the actual integral of G2. And this is essentially modular of weight of negative weight equal to minus 2r plus 2, I think. But it's not quite, so the difference. Yeah, so okay, let me tell you more about this later. Okay, so what I'd like to say is that, so in fact, we introduced these objects in 2018 and studied their study expansion, but in fact, the fact that the coefficients are multiples of the values already comes from something which was known in 2014 by Brodel, Schlotterer, Mafra, and Niels Mattes. And it's the fact that these open string amplitudes are elliptic multiples of the values. So in particular, homomorphic web functions are elliptic multiples of the values. I'm not telling you what they are, elliptic multiples of the values, but let's say there are special cases of iterated integrals. So here, instead of taking one integration like this, you take iterated integrations of Eisenstein series. But it's a small, I mean, it's a subset of this. And probably Aaron knows more about this because I think you studied integration algebra, which selects elliptic multiples. Okay, so anyways, so this is the open string guys. The closed string guys, they are in the very simplest case, they're just non-homomorphic Eisenstein series, as already mentioned today by Daniele. Polygon case, and let me do the expansion of the cosmos. Simple 2 vertex 1. It's like this. So you have odd Riemann zeta, but you don't have the even ones. Expansion. This is not coincidence. And now you're expanding this variable y, which is okay. This is not a definition of y. So there is not just one type. So this is the imaginary part of tau. Minus 2 pi. It's minus 2 pi imaginary part of tau. Okay. And the theorem, which I proved partly in my PhD thesis, and then so this modular graph function has an expansion like this, which depends on the number of edges of gamma. And I could only prove in my PhD thesis that these numbers are special values of multiple polylog at roots of unity. And then Eric Panzer refined this and proved that they're actually multiples of the values, so special values at 1. But in fact, I computed a lot of these coefficients, and I conjectured that they should be single value multiples of the values. I even found the reducible ones, zeta 3, pi 3, and so on. And the status of this conjecture is still an open conjecture, which is now known only for graphs up to 2 loops, thanks to Luke and Luke. So these would be the CABC that were mentioned by Daniel today. And also in a different direction, they're known for all 2 vertex graphs, so any number of loops, but just 2 vertices. This was proven essentially at the same time by myself and Zagier and Docker and Green, but one of the proofs in our paper, we have 2 proofs. One of the proofs was found by Zagier over 10 years ago. So I think this is a theorem by Zagier. And the 2 proofs appear on the puzzle together with. By now, I think there are 4 or 5 proofs. Okay, and I would like to conclude by comparing Gene's one open and closed strings. So the expectation is that the closed string should be single valued analog of the open strings. So there should be also this kind of KLT-like relation, double relations. But the single valued period theory is much more complicated in Gene's one. So we're not quite able to do this at the moment. Francis Brown constructed using his theories, single-valued periods, a class of real analytic modular forms which are single-valued analogs of elliptic multiples of values. whose asymptotic expansion are single value multiples of the value. So this looks good. But we are not able yet to prove that modular graph functions belong to this case. So that's a conjecture stated by Francis. And let me now compare again modular and the holomorphic graph function expansion to introduce the second conjecture. This is asymptotic expansion, and if you map t to y, you keep the rational numbers the same, and you map zeta 2 to 0 and zeta 3 to twice zeta 3, which is the usual thing to do for a single value projection. Then you go from holomorphic to modular very easily. So this looks promising. That's why we introduced this holomorphic graph function in the first place. So we conjectured in 2018 that at least for the first Laurent polynomial, you can just apply the single value projection term by term and go from holomorphic to modular graph functions if you have the same graph. And this was proven in my paper with done in 2019 for n equal to what is n here is the number of vertices. For all the two vertices, holomorphic and modular graph functions, we could demonstrate this conjecture too. And so in particular, by this single value projection formalism, we also have some kind of double copy relations between the generating functions of the Laurent polynomials, which is very promising. Now, should be able, hopefully, to extend this to the whole amplitude and then to higher number of points. But this is already some promising thing towards KLT engines.
Federico, in your 2019 paper, you found two generating series for all of these love.
Yeah.
And you proved that a single value map of the open.
Yeah.
This is standard.
Okay, so now the conclusion is in Genus 0 we can go from here to here and explain how. I hope you understood the definition is not so explicit, but more or less you have an idea of what single value MCDs are. Now here you can hopefully go from holomorphic to modular graph functions using this kind of projections. And then you can go from elliptic MCDs hopefully to modular graph functions by Brown's theory. And as I said, these are two special cases of iterated integrals of Eisenstein series. So this is something, so in single value periods, if you have a modular form and you apply the single value projection, you kind of solve the modularity issues. And you have something homomorphic and non-modular, you get to something modular and non-homomorphic. That's something that you see a lot in theory of modular forms, and that's very nicely explained, at least in this case, by the single value period form. And then it would be interesting to do something similar in higher genus, and first you need to define higher genus analogs of these multiple zeta values. And so I'm working on the mathematical side of this. My project with Benjamin Arrigues is defining higher genus analogs of multiple zeta values. And there is also some work for the physicists to do to put in here, but hopefully once this is done, you can try to relate two things in the same way. Yes, thanks a lot.
Very much. Questions?
So, is there some geometrical meaning of double copy relations? You go from open strings.
I think there's a picture that physicists study minds. So you have this string amplitude in genus 0. The disk, you represent it like this, and you have a half sphere. And you have the other out sphere. And you put them together to form a geometric form. That's the picture that physicists have in mind, but it's some kind of guidelines, but it's a little bit misleading, I think, because the real way how you go, from here to this amplitude in string theory to define the open string amplitude is not really, you're not really cutting this in half. It's rather some involution you're applying on the sphere. And I think in the more exotic topologies, you cannot really think in. I mean, I'm not very good in these kind of pictures, but I'm not sure that that's the right way of looking at this. Okay.
what you were saying, is that okay?
Then you said it.
What it's working with complex numbers.
Yeah. In which context is true?
Generally talk, talking about crystal. So,
Sure. So as I said, there are analogs of periodic analogs of periods, these periodic periods, but I think not much is known about them. So I'm not sure. As I said, I'm not even sure you can have an integral representation of these periodic periods in general.
So you show this commutative diagram, homologies and so on. As Philip is saying, so if you do the periodic one, you can have a complex at infinity. So is there some adelic version of these homologies that you could imagine having this over the adels instead?
So okay, so first of all, let me write down the periodic, the definition of periodic periods. So maybe we're on the same page. So as I said, so you have H around. Then you have the comparison isomorphism. Now, in tensor with you have the comparison with HM crystalline, and then yeah. And then here you have the Frobenius. This is an evolution of crystalline homology. And then you go back. So this comparison compared to -1. Efficient and circuit. So this is single value. It's not single value. It's just the periodic in periodic view. Sorry, it's QP. I think it is. I think it is. I can check. Okay, and then the question is, can we repeat the same kind of computation that were shown using these periodic periods, in particular, all these properties given by Francis Brown for the single value periods, do they still hold for periodic periods? I'm not sure somebody really studied this. So, so there is a recent work by Giuseppe Ancona and Dragos Pratila, who are studying these periodic periods defined in this way. Because I think most of what was done on periodic periods is more on this definition of Fontaine, which is different from this one. So I may be wrong, but I think it would be interesting to do what you suggest, but we don't have the instruments, so we have to develop some. Yeah, that's a good point. So, yeah, that's a good point. It would be very interesting.
Well, Breckley and Freund did periodic versions of the Sienna Amplitude. Also with Whitlam, some papers many years ago. Yes.
I mean, what is the physical meaning?
Well, I think that was not clear at the time, but I mean, that partly has been taken up now by this, there's this sort of periodic ADS CFT correspondence where some of those things are coming back up again. I don't know if one should view that as a toy model or something.
I don't think about it.
Yeah. Yes. Yeah.
So by the way, it was also interesting to see how this single value period format is related to the ADS.
Yeah.
So, can you, are there some relations that are known? Like, can you, in some cases, figure out some of the relations in this period. One's just coming from these multiple data.
So you're asking about just multiplicity values, not the general view.
Yeah. For those, can you use these expressions?
Oh, well,
Can you break
all no, that's impossible. So there are, okay. So by the period conjecture of Grothendieck, you know what should be all the possible relation between different period representation of the same period. So different integral representation of the same period. And these are just given by so there is linearity, integrality, so changes of variables, stokes. That's all you can. Now you are asking in multiplicity value case. I don't think you can use that to predict the relations of multiplicity value because those relations are very mysterious and difficult to get. So if you have two different integral representations of the same number, even if you know it's the same number, it's almost hopeless to try to prove using just this set of identities that you are allowed to use that they're the same number. It's very difficult. So I don't think that's the right way to look at the relations between multiplicity values.
Sorry, so I was saying something like you have an integral representation in terms of slices that series maybe, and you can then use the fact that you know this.
What do you mean the elliptic? So the elliptic multiplicity values are iterated integrals of Eisenstein series. But the multiplicity values are just numbers given by integrals like this. So 0, 1 to some power n, and then you have differential forms like, oh, maybe it is 1, and you have typically dpi over dpi or dpj 1 minus 50. So you have problems of forms like this.
Could you say something about how this cosmic Galois group fits into this, or what that is, or what is the idea of that?
I cannot really
You cannot
say
say,
about
okay.
that.
Okay.
The right person. So maybe
Francis Brown was trying to explain a little bit over dinner, with the conference dinner, and I don't really.
So first of all, this idea was born in the context of quantum peculiarities, and I'm not sure if there's if anyone ever thought about string theory and because how we would connect to this thing. So I think it's not really a theory, which is so the idea is that so whenever you have a category of motifs, then there is also a Tanakian category, there is a group, Tanakian group, which is called the Galo group of the periods. And this will just send one period to another period. And then he would like, I think people would like to define a category of finite motifs, and then because they realize that the periods appearing in finite amplitudes is quite a restricted set of numbers. You don't get all the multiplicity values, you get a very small subset. And one way to prove that would be decided to prove that you are in a certain category of motifs and there is this action. They need to be.
Yeah, no further questions. Let's thank Federico again.
So this is asking, modular forms as a brain generator. So if you do that in